electron affinity. I hate this definition because it doesn't really fit the situation. It's defined as energy required to add an electron, and so here's your little atom, here's the electron, here's the energy that you're putting in, and if it works, you form a negative, right? You would form an anion. You'd be sticking that electron onto the atom, forming a negative charge. But the strange thing is, and the reason I don't like the definition, is you're talking about like that, like it's an energy input. You put in some energy and you can make that electron stick. There is nobody that does that. There's not one element that works that way. They either want that electron, and gaining that electron makes them more stable, and they release energy because you made them more stable, or they simply won't take it. The electron's not going to stick if it doesn't make it more stable. So your values are either 0 if they don't gain it, or there's some negative value because it's releasing rather than requiring. So I'm going to tweak the definition just a little, or at least the way we explain it. Metals or non-metals? Who's going to be better at this? You're forming a negative, that would be non-metals. So I'm not going to say highest or lowest, I'm going to say most favorable. Non-metals have very favorable electron affinities, and fluorine is the best. And atomic size. Some sources talk about atomic radius and others talk about diameter, but still you're talking about the size of the atom. Non-metals, by virtue of having a lot of attractive force, tend to draw their electrons in closer to the nucleus. Metals that don't have a whole lot of force, the electrons tend to stray, and that makes the atoms larger. Non-metals tend to be small. And of the reactive elements, fluorine is the smallest. Not counting noble gases, not counting hydrogen, of the reactive ones, fluorine is the smallest. Carbon or nitrogen? Which one is smaller? Nitrogen. Nitrogen or phosphorus? Which one is smaller? Nitrogen. And you can still gauge all that proximity-wise on your periodic table toward fluorine. Do you see that pattern? If you memorized this, then the patterns are not that bad. Go ahead.
So oxygen and chlorine are both one away from fluorine. Which one would be?
In that situation where you're comparing like oxygen and chlorine, Let's think just a minute about configuration, electron configuration. Oxygen is only 2 energy levels big, but chlorine is 3. And that size, that extra layer, diminishes the force. And so if you're comparing ones that are essentially equidistant, this is one space away, then go with the one with fewer energy levels. Fluorine is your highest electronegativity and so forth, but oxygen is a very close second. More so than chlorine, for sure. Other question? All right. There's a small section here, exceptions and irregularities. Throw that out. We're not going to worry about that. I'm more concerned with knowing the patterns than the exceptions to the patterns. But that one small section you can omit. Next thing to look at then turn to the page on Lewis dot symbols. And this is alluding back to electron configuration. Write out the complete configuration for sodium, not abbreviated. Write out the electron configuration for sodium. Did anybody not sign the roll sheet? Is this what you got? Right. And then we said that we could abbreviate things because what really, really mattered, it wasn't so much where all the electrons are. I mean, that's important. But what really mattered most was that valence part. And so we started abbreviating things as far as core and valence and other electrons that were beyond core, but not valence. And so that led us into abbreviated configurations, which for sodium would look like this. Neon core, abbreviating the first 10. There's one more electron. That's in the third row of the S block. 3s sublevel, one electron present. Question about that? Lewis dot notation is going a little bit further and taking this abbreviated configuration and abbreviating it again. To where the point is going forward into what we call Lewis structures and showing the bonding of molecules, what matters is that there's one valence electron. It's not so much important that that's in third level as opposed to fourth or fifth or sixth level. So converting that abbreviated configuration into a Lewis symbol would look like this, where that one little dot represents one valence electron, and that's what we really need to know about sodium. When we get into predicting bonds and things of that sort, shapes of molecules, that's what matters. Now between the dotted lines, you've got the beginnings of a little chart. We're going to flesh this out somewhat right now. Later, exam 3, we'll be coming back to it and adding more information to it. But this little chart is going to be a valuable summary of a lot of this Lewis structure related information. How many valence electrons does lithium have? One. Valence electrons, lithium has one. Beryllium, boron, 3, and then you just keep right on counting across those A columns, right? Because that Roman numeral A, the Roman numeral is your valence electrons. Now what I'm putting up here is not just for these elements, it's for everybody in these columns, okay? So this is all of your alkali metals, and even hydrogen actually, and beryllium, everybody in that alkaline earth metal column. So it's everybody in the columns. This is just, I guess, essentially the top one in each column. And then putting the valence electrons picture-wise into your Lewis symbol, you're going to have one dot on the lithium, 2 on the beryllium, 3 on the boron, 4 on the carbon, and so forth. Now I am spreading these out in somewhat of a pattern.
Does it matter where to put this dot?
Not really. This is one of those things that used to be around the symbol. I'm just going to generically do X for the moment. But if you think about valence, you've got an S and you've got a set of P. And so that's 4 orbitals. And the way that you would fill electrons would be, don't write this down, okay? This is background, okay? First electron, second electron. You would fill that up. Then it was third, fourth, fifth. Then you went back and paired, correct? It used to be that you would start, wherever you started, you'd put 2 of them in together, and that represented the S. And then for these other locations, which represent P, it would be 1, 2, 3, and then another lap through 1, 2, 3. Okay? That's really not important as long as you do show that they are somewhat distributed. Okay, for example, like here with nitrogen, you know there's no more than 2 electrons per orbital ever, correct? So don't do this. You're not going to have all 5 electrons lumped up together on one side of the atom. That don't happen. Spread them out. You do need to spread them out. But as far as like with nitrogen, where do you put the paired, where do you put the ones, it don't matter.
On beryllium, if we have them right there together, it would be spread out.
Doesn't matter. So I guess what I'm saying is no more than 2 at any spot, because that would just be flat out impossible. But like beryllium, if you wanted to do 2 here, that's fine. If you wanted to do 2 here, that's fine. If you wanted to do 1 here and 1 there, I'm okay with that too. Because once they start bonding, that's actually what happens. They'll split apart. But distribute them. No more than 2 per position. Because 2 is the maximum for an orbital. Does that answer your question? Okay. Other question about that? The dot symbols. All right. Ionic charges. When we were dealing with electron configuration and forming cations, we talked about the valence electrons getting removed. For lithium, emptying out that S sublevel is going to be 1 electron gone, and that would be a +1 charge. Everybody in column 1A formed exclusively a +1 charge. In 2A, it's +2. That's very reliable, very dependable. No other options. Starting with the non-metals, like neon, neon's got that perfect octet already. It's not going to form charges. It doesn't need any more, so it won't form negative charges, and it's certainly not going to part with what it's got, because that's perfectly filled and symmetrical. Therefore, 0. No compounds, no charges. But as you count your way over, here's fluorine, strong attraction for electrons, and it's got a vacancy right about there. 1 vacancy. So gaining 1 electron would make it a -1 charge. Oxygen has 2 vacancies. And filling each of those would make it a -2 charge. Nitrogen, -3. Now, I'm not listing anything for boron and carbon, because first of all, they don't often form charges, and second, when they do, there's a variety of things they could be. But what's up there for charges, it's what's reliable and dependable and always going to be. Oxygen is going to be a -2. Fluorine is going to be a -1. You'll never see fluorine as a -2. Those are the charges that are regular and dependable. Now, covalent bonds. Preferred number of covalent bonds. When we talked about covalent bonding, I said it was always a pair of electrons. And usually it's each atom contributing an electron to form that pair. And so an electron from this atom and an electron from this atom, they each get pitched in, and that's where the pair comes from. For the most part, it's 1 + 1 makes 2. So if here's our fluorine, with the vacancy, and here's our sodium with 1 electron, who is fluorine competing against? A metal. That electron gets completely taken away. There's your sodium ion, There's your fluoride. But if you've got fluorine competing against another non-metal, just to keep it simple, let's say it's another fluorine, then he's not taking an electron from this guy, right? That's not possible. But he tries. And so does that. And so what you end up with is that pair of electrons that are shared between them. And the net result is, through sharing, it's gained access to one more electron. By forming one bond, it's gained access to one more electron. Because what it comes down to, if you look at that symbol for fluorine, it's got one spot to fill, and it doesn't matter whether it fills it ionically or covalently, it's got to fill that spot. Fluorine will form one covalent bond. Guess how many oxygen atoms? And nitrogen. And neon. 0. Now the metals over here, like lithium and beryllium, it's extremely rare that they form covalent bonds. But in those very, very few cases that they do, it's one bond and two bonds. Do you see how that runs exactly parallel to your ionic charge? Nitrogen needs access to 3 more electrons. That'll be a -3 if it's in competition with a metal, or 3 covalent bonds if it's in competition with a non-metal. But either way, it's got to gain access to 3 more. And that's the way we do it. Boron and carbon here, 3 and 4 bonds respectively. So the pattern for bonds is, as you read across the row, you count up to 4 and then you start counting back down again. Question with that? And the last line here is the octet. We start with lithium. And like I said, it's very rare that it would form a covalent bond. But if this is its 1 electron, and this were a situation where it would covalently bond, then it would take its 1 electron with somebody else's 1 electron, and that would make the pair, which would give it 2 valence electrons at that point, access to 2 valence electrons. And that's all it's capable of. Now, octet literally means a group of 8, but for lithium and the others in that column, their octet is 2. And I know grammatically that doesn't make any sense, but I can call it that if I want to, because octet, in addition to meaning a group of 8, chemically octet means stability. And 2 electrons is what makes lithium stable in that sense. It's impossible for it to get 8. But taking its 1 and pairing that with somebody else's 1 would make 2 valence electrons. That gives it its 1 covalent bond. That's what makes it stable. So the things in column 1A have an octet of 2 electrons. That's what they try to achieve. Beryllium, taking its 2, each with somebody else's, would give it 4 electrons. So beryllium and the other things in column 2A have an octet of 4 electrons. When bonding covalently, it will form 2 bonds, and that gives it a total of 4 valence electrons. More than that is just simply not possible. It doesn't have the equipment to form enough bonds to get to a true octet of 8. The octet for boron is what?
6.
Carbon? 8. Carbon has 4 valence electrons. It's 4 with 4 from other sources makes a total of 8. And then we get to nitrogen. With these 3 vacancies. 1 electron here, 1 electron here, 1 electron here, forming those 3 bonds that we already talked about. There's no tendency to bond up here, really. Sometimes it can be forced to, but it's not going to want to. It wants to form 3 bonds. And because it has that one pair that it's not sharing at all, it's octet of 6. Similar for oxygen, similar for fluorine, similar for neither. You count up to 8, and then it stays 8 forever after. Because once you hit that true octet, it plateaus. Question about that? But the atoms like lithium, beryllium, and boron don't have the ability to reach a true octet. Because to get one, you got to chip in one. And they don't have enough of their own to put in to get a full true octet. So 2, 4, and 6 for those respectively. Question about anything on that chart? You need to know that chart. You need to know the behavior of these elements. Ionically, covalently, what their octets are. It's important right now. It's going to be really, really important when we get to exam 3. Because at that point, we're not just looking at carbon or oxygen. We're looking at 3-dimensional shapes of carbon dioxide and things like that. And to be able to get that, you've got to go through the information on this chart. So we're never getting away from that, and we're actually going to be building on to it. So, question about anything on that chart? You've been going over chemical nomenclature in the lab. Do you have any questions on that?
Can you just explain what it does?
Anything in particular?
Well, I'm not exactly remembering what it is right now.
Okay. All right, let's start with this. categorize each of these as being either ionic or covalent. The thing with chemical nomenclature is you're taking formulas and writing names, like NaCl becomes sodium chloride, or vice versa, converting the name to a formula. And the naming system is different for covalent things than it is for ionic things. So before you want to even try to put a name to something, you've got to know what you're dealing with, because the systems work differently. And the key to that we already talked about back when we were doing ionic bonding. Metal or ammonium. With non-metals gave you ionic bonding. So you tell what kind of compound you've got by looking at what kind of elements you got. Go ahead and categorize these. There's two major problems that students typically have with nomenclature. One is just the dizzying array of polyatomic ions that you've got to deal with, like chlorate and chloride and hypochlorite and things like that. Have you done that one in lab yet? Polyatomic anions? No? All right. Consider that foreshadowing. It's just the huge number of polyatomic anions that makes it complex. But the other problem that people have is they'll name ionic things by the covalent system, or vice versa. And that's because they're trying to jump to the name without having categorized it first. Because you can have very parallel looking formulas, and they get named very differently, depending upon whether it's ionic or covalent. CaCl2, ionic or covalent? Ionic. This one. This one. Okay. That's the ammonium thing. And this one? P2O5. U2O5. CUS. And Cu2S. Yeah. All right. So what we'll do now is, for what we've got there on the center board, we're going to go ahead and do the covalent ones first. And then we'll come back for the ionics. But the covalent ones, the two things about the naming system is that the last element gets an IDE in there. You change the ending to be IDE.